This is Boyles' law and Charles' law calculations. Boyles' law and Charles' law are used to explain the relationship of temperature and pressure on the volume of a gas. Boyles' law states that the volume of a fixed mass of gas varies inversely with the pressure at constant temperature. So this means that if the pressure of gas at constant temperature changes, the volume will change too, but the product of pressure and volume will remain constant for a fixed mass of gas. Then the formula will be P1V1, that's the initial pressure and volume, equal to P2V2, the final pressure and volume. So this is inverse relationship. That's as volume is increasing, the pressure is decreasing, and as the pressure is increasing, the volume is decreasing. So you see the shape of the graph. So let's look at this in a very practical way. We are looking at the relationship between volume and pressure at constant temperature. Okay. So we have to have some particles of gas. That's heavy and light. This time it doesn't matter. We want to have just some gas in here. And then we are holding the temperature constant. And we want to know what will happen. We want to know the relationship between volume and pressure. So what I'll do now is to increase the volume. As we increase the volume, we see what happens to the pressure. So I'm decreasing the volume. Look at it. As the volume is decreased, the pressure is increased. That's inverse relationship. So if I increase the volume, the pressure decreases. Remember, this fixed amount of gas, so the number of moles is constant here, and the temperature is also constant. So that's Boyles' law. So we see how the particles are colliding, the impact on the walls, the force they're exerting on the walls of the container. There'll be more force. If we decrease the volume, you see the difference, the collision, the way it strikes the wall compared to if the volume is increased. And you compare that to the temperature. I mean to the volume. You are checking volume and pressure. So kinetic molecular theory and pressure is the pressure of the gas is caused by molecules of the gas striking the walls of the container. If the gas is compressed to half the volume it had, twice as many molecules are present in any given volume, the pressure of the gas will double. Okay, the pressure of the gas will double. So let's look at an example, do calculation to see how this works. So let's look at this example. A balloon filled with helium has a volume of 457 milliliter at 762 millimeter mercury. After the balloon is released, it reaches an altitude of 6.3 kilometers, where the pressure is only 355 millimeter mercury. What is the volume of the balloon at this altitude? So in solving this problem, you have to analyze the question. Try to understand what the question is telling you to do. Don't jump into it. So you have to look at what is given here a balloon filled with helium has a volume of, so the initial volume is 457 milliliter at 762 millimeter mercury. Millimeter mercury is unit for pressure. So 762 millimeter mercury. Okay. After the balloon is released, it reaches an altitude of 6.3 kilometers, where the pressure is only 355. So the final pressure is 355 millimeter mercury. That's the final pressure. Then what is the volume of the balloon at this altitude? So what is the final volume? This is, I think, is straightforward question. So this is relationship between pressure and volume. Okay, pressure and volume. So the temperature is constant. Sometimes it's not clearly stated in the question, but from all you know, you will notice that there's no change in temperature. So since it's Boyles law, we are using P1V1 equals to P2V2. We are solving for V2, so we have to isolate V2. We divide by P2 over P2. This we cross out, so V2 is by itself. If you like, I can move it to the right, it doesn't matter. So you plug in the numbers. P1 is 762 millimeter. You must include their units. And V1 is 457 milliliter. Okay. Divide by P2, which is 355 millimeter mercury. All of this is equal to V2. So this we cross out. You punch this in your calculator. Okay, the answer will be to three significant figures. So V2 will be 981 milliliter. Okay. 981. Sometimes your teacher may tell you to change it to liters. Okay. So that's the answer, example to that. So now you check if it makes sense. The pressure, initial pressure is at 762 at a volume of this. Now, when you read the altitude, the pressure dropped. You see that? When the pressure dropped, the volume increased. That's how you know that it makes sense. If it doesn't make sense, you have to go back and check what you did wrong. Pause the video and do this practice question. Pause the video and do this practice question. It says, under a pressure of 623 millimeter mercury, a confined gas has a volume of 335 milliliter. If the pressure is increased until the gas has a volume of 252 milliliter, what is the new pressure, assuming the temperature remains constant? Here is clearly telling you that the temperature remains constant. Please pause and solve. Hopefully you did it. So the question again, under a pressure of 623 millimeter mercury. So under the pressure, the initial pressure is 623 millimeter mercury. A confined gas has a volume of 335. So initial volume is 335 milliliter. Then if the pressure is increased until the gas has a volume of that, Okay. Volume, the final volume is 252 milliliter. What is the new pressure? That pressure will be the new P2, okay? So again, it's still Boyles law, okay? So this time we want to figure out the P2. So we divide both sides by V2. So P1 is 623 millimeter mercury multiplied by V1, 335 milliliter, all over V2 final volume 252 millimeter all over P2. So milliliter will cross out. You must keep your units and show how it's crossed out. Then the P2, we plug it in calculator. P2 is equal to 828, three significant figures again. 828 millimeter mercury, because that's unit of pressure. That's it. Hope you did it right. Cheap. Okay. We increase the temperature. The volume is increased. We decrease the temperature. The volume is decreased. Direct relationship. Okay. Let's look at this example. A quantity of gas occupies a volume of 506 cubic centimeter at a temperature of 147 degrees Celsius. Assuming that its pressure remains constant, at what temperature will the volume of the gas be 604 cubic centimeter? The first thing you check here is to analyze the question. And analyzing the question, you can see clearly that this is a relationship between volume and temperature. It's clearly stated, volume and temperature. It clearly tells you that it's at a constant pressure. So you look at what we have. We have a quantity of gas occupied a volume of that initial volume is 506 cubic centimeter at a temperature of, so initial temperature is 147 degrees Celsius. I like to do this immediately because it's easy to forget. Okay, it's easy to forget, which will be like 420. Take care of it immediately. And then at a constant pressure is constant, then it says, assuming that the pressure remains constant, at what temperature? So the final temperature, we do not know. With the volume of the gas be 604. So the final volume is 604 cubic centimeter. Again, this is Charles' law. So V1 over T1 equal to V2 over T2. Okay, now we want T2. So V1, we cross multiply V1 T1, V2 T1. Okay, we want to isolate T2. We divide by this. Okay, that means T2 will be equal to, we know V2, 604 cubic centimeter times T1, 420 K divided by V1, 506 cubic centimeter. This will cross out. So T2 will be, you plug it in, will be, let's see, make sure. Here's my calculator. It will be 501 Kelvin. Again, 3 significant figures. Okay, that's it. So here, kinetic molecular theory, and doubling the Kelvin temperature of a gas doubles the average kinetic energy of its molecules. So if volume is doubled, Kelvin temperature will double at constant pressure. So in every calculation you compare, like what you just did, compare and see the relationship and see if it makes sense. So in these faster moving molecules, strike the walls of the container more often. It strikes with the walls of the container with more force. So when the temperature increases, the particles are moving faster, or the molecules are moving faster, and there'll be more force on the walls of the container. Okay. Gay-Lussac's law is similar to Charles' law. I don't have any calculation on this, but it's very, very similar. When the temperature of a sample of gas in a rigid container is increased, the pressure of the gas increases as well. So the increase in kinetic energy results in the molecules of gas striking the walls of the container with more force, resulting in a greater pressure. So this is very, very, even the calculation, they're very similar. The only difference here is that the volume is constant. Okay, that's the only difference, but it's very similar to Charles' law. Both the calculation and everything is very similar. I want you to look at these practice questions, pause the video and try them and see if it makes sense. Look at these practice questions. Try your best. To get it right. Let's try the first one. The gas in a balloon occupies 2.25 liters at 298 Kelvin. At what temperature will the balloon expand to 350 liters? Okay. We know the initial volume, the initial temperature. The initial volume is 2.25 liters. Initial temperature is 298 Kelvin. At what temperature, that's final temperature, will the balloon expand to final volume of 3.50 liter? Okay, again, it's not obvious. It didn't tell you what is constant, but from experience, you know that here, pressure is constant. So V1 over T1 equal to V2 over T2. Again, we are calculating T2, which is similar to what we've done before. So V1 T2 equal to V2 T1. We divide by V1 over V1, cross this out. So T2 will be V2 3.50 liters times T1 298 Kelvin over V1 2.25 liters. These 2 liters we cancel. Then we calculate, use a calculator. So I'm getting T2 is 464 Kelvin. That's it. 464 Kelvin. The answers to the last 2, 331 Kelvin. The last one is 608 kilopascal. So here, the second one, you don't forget to convert this to Kelvin. You have to convert this to Kelvin. Then it's pretty straightforward. Nothing really very challenging here. I hope this makes sense. Thank you.